Welcome to another miraX video tutorial. In this session, we'll explore one of the end products of the Interreg Buffer Plus project, the Peatland Subsidence tool. But before we dive into the interface and run some simulations, let's briefly review the main concepts behind this tool. Peat subsidence refers to the gradual sinking of peatland surfaces. This is a slow, spatially variable process driven largely by the drying and decomposition of peat soils after groundwater levels are lowered. When peatlands are drained, for example, to enable agriculture, the peat above the groundwater table becomes exposed to oxygen. This oxygen exposure accelerates microbial decomposition and oxidation of the organic material, causing the peat to shrink and the ground surface to sink. The miraX subsidence tool is designed to help users better understand this process in the Duurswold peatland area in the Netherlands. It allows you to simulate how peat subsidence evolves under different surface water management scenarios using a simple numerical model. The tool also estimates the amount of CO2 emissions that can be avoided by raising groundwater levels and slowing peat oxidation, effectively showing the climate benefits of improved water management. The subsidence model running behind miraX uses two main types of input data. First, it relies on borehole measurements collected across the study area for a defined reference year. This baseline dataset describes both the thickness and elevation of the peat layers, as well as the average lowest groundwater levels, or GLG. These parameters form the foundation of the model and allow us to estimate how much peat is exposed to oxidation under current conditions. Second, the model uses a change in surface water level, specifically, an increment in water level in the area's drainage ditches, to represent a surface water management scenario. This increment acts as the driver of change in the model. Higher ditch water levels lead to higher groundwater levels, which in turn reduce the amount of peat exposed to air. It's important to note that the model does not simulate the engineering measures or interventions required to achieve these water level increases. It simply evaluates their impact once applied. These two inputs together allow the subsidence tool to estimate future peat subsidence, future GLG, future elevation, future peat thickness, and calculate the CO2 emissions that could be avoided by raising groundwater levels. Let's now take a moment to get familiar with the miraX interface. When you open the Duurswold project in miraX, the map automatically centers on the study area. In this case, you're looking at the Duurswold peatland region in the northeast of the Netherlands. The layer currently displayed shows the terrain elevation for the reference year 2018. This is the base layer used by the subsidence model to calculate future surface elevations and compare them with the original state. Areas with higher or lower elevation are visualized with different colors, allowing you to quickly spot topographic variations across the peatland. On the right-hand side of the screen, you'll find the tool icons, including the subsidence tool that we'll use shortly. On the left, you have the Layers panel, where you can browse, show, or hide both project layers and any model outputs you generate. The actual borehole information used by the model is available in this panel. Now let's walk through how to run a simulation. Go to the right-hand toolbar and click the subsidence tool icon. A dialog window will appear with several model parameters. Layer, the elevation map for the reference year. Year, the target year of the simulation. Yearly loss, the proportion of peat lost per year due to degradation. Surface water increment, a uniform rise in ditch water levels across the area, in meters. And recharge factor, the percentage of that increment that effectively raises the groundwater table. Let's run the baseline for 2050. Normally, the model generates the baseline automatically in the background, but here we run it manually for demonstration purposes. Set the year to 2050 and leave the surface water increment at 0. This means no change from current conditions. Keep all other parameters as default and click Get Subsidence. The tool calculates projected peat subsidence, elevation, peat thickness, and groundwater depth for 2050 without any changes in surface water management. In the results pop-up, you'll see that avoided CO2 emissions are 0, because we are comparing the baseline to itself. The outputs are added to the User Layers panel, where you can inspect subsidence, groundwater depth, peat thickness, elevation, and avoided CO2 emissions. Next, let's run a scenario for 2050 with improved water management. Open the subsidence tool again, set the year to 2050, and this time increase the surface water by 0.2 meters. Keep all other parameters the same, then click Get Subsidence. The model now calculates peat and groundwater conditions under the raised water level and automatically compares them to the baseline. You should notice less subsidence, shallower groundwater, more remaining peat, slightly higher future elevation, and positive avoided CO2 emissions, reflecting reduced peat oxidation from the water level improvement. Again, these results are added to the user layers panel so you can visually inspect them. This demonstration shows how the subsidence tool can help decision-makers explore the impact of water management strategies on peat subsidence and CO2 emissions in Duurswold peatland. For more details on the model, its assumptions and limitations, please consult the user manual. Thanks for watching.